College students today face unprecedented levels of stress, anxiety, and depression, challenges that have only intensified during the global pandemic. With mental health crises on the rise and limited access to clinical care, early detection is more urgent than ever. But what if we could use everyday wearable devices, like Fitbits, not just to track steps or sleep, but to detect early signs of mental illness? This is exactly what our research explores, using Fitbit data collected from college students during the early pandemic months to build machine learning models that screen for depression, anxiety, and stress, non-invasively, continuously, and at scale. We collected a unique dataset called StudentMEH from 166 undergraduate students aged 18 to 23. Over a year-long period, from May 2020 to May 2021, participants wore Fitbits that captured 5 key physiological modalities: heart rate, sleep stages, step count, distance traveled, and calories burned. These were paired with self-reported mental health assessments using 3 gold standard tools: the CES-D10 for depression, the SDAI for state anxiety, and the PSS-4 for perceived stress. Importantly, we applied clinically validated cutoffs. A CES-D score of 10 or higher indicated depression, 40 or more on the SDAI meant clinical anxiety, and 6 or above on the PSS-4 signaled high stress. The results: over half of our participants, 53.7% for depression, 60.6% for anxiety, and 60.8% for stress, screened positive. These numbers reflect a real and pressing public health issue. But the real innovation lies in how we process the data. Raw Fitbit data comes in high-frequency bursts: heart rate every 5 seconds, steps and sleep every minute. To make this usable for machine learning, we aggregated it into weekly time series across multiple granularities: 1 hour, 4 hour, 6 hour, 8 hour, 12 hour, and full day, 24-hour intervals. Why does granularity matter? Because mental health symptoms aren't static. Anxiety spikes can occur within hours. Sleep disruptions can shift dramatically between day and night. By testing different time windows, we could identify the optimal resolution for detecting each condition. Then came the modeling phase. We evaluated 6 popular machine learning algorithms: decision tree, logistic regression, random forest, support vector machine, XGBoost, and AdaBoost. Each model was trained to classify whether a student was experiencing depression, anxiety, or stress, based on the aggregated Fitbit features. But we didn't stop at raw data. We transformed each week's time series into a rich set of statistical features: mean, median, standard deviation, entropy, percentiles, range, interquartile range, and more. This conversion turned variable length time series into fixed-size vectors, making them compatible with traditional classifiers while preserving meaningful patterns. After rigorous cross-validation, using a leave one participant out strategy to ensure robustness, we found something striking. Sleep data was the strongest predictor of depression, achieving an F1 score of 0.78 with an SVM model at a 4-hour aggregation level. That's nearly 80% precision in identifying depressive symptoms from sleep consistency and deep sleep duration. For anxiety, step count emerged as the top signal. A random forest model using 6-hour aggregated step data reached an F1 of 0.83, the highest of any condition. This suggests that physical activity patterns, especially their variability and entropy, are powerful indicators of anxiety, likely reflecting restlessness or avoidance behaviors. And for stress, the calories burned metric stood out. At a 4-hour aggregation interval, AdaBoost achieved an F1 of 0.81, showing that energy expenditure patterns, how people move when they move and how much they burn, can capture stress-related physiological arousal. What's more, we discovered that combining all modalities didn't improve performance. In fact, it often hurt it. This implies that different data streams may carry conflicting signals, and indiscriminate fusion can degrade model accuracy. Instead, we recommend selective, condition-specific modeling. Our feature importance analysis confirmed this. For depression, sleep duration and heart rate variability were dominant. For anxiety, step entropy and median step count were key. And for stress, heart rate, standard deviation, and peak intensity were the most predictive. These findings point to a deeper truth: mental health isn't one-size-fits-all. Depression is tied to disrupted sleep cycles. Anxiety shows up in erratic movement patterns. Stress manifests in physiological instability. And each condition responds best to different data types and time granularities. We also found that tree-based ensembles, random forest, and AdaBoost consistently outperformed other models, especially in high-variance, nonlinear domains like mental health. Their ability to capture complex interactions between features makes them ideal for this kind of task. Now, let's be clear, this isn't about replacing clinicians. It's about augmenting care. A Fitbit isn't a diagnosis, but it can flag early warning signs, like a sudden drop in sleep quality or a spike in heart rate variability, triggering timely interventions. Imagine a university student who's quietly struggling. Their Fitbit detects a week of fragmented sleep, reduced steps, and elevated resting heart rate. The system flags this as high stress. A gentle push notification suggests a mindfulness app, or a telehealth counselor is automatically scheduled. This is proactive, personalized, scalable mental health support. Of course, ethical considerations are paramount. Students must give informed consent. Data must be anonymized. Institutions must ensure transparency and privacy. devices should remain tools for empowerment, not surveillance. And while our dataset has limitations, like participant compliance and Fitbit's sensor accuracy, we mitigated these by using weekly segmentation and rigorous imputation. Future work will explore intrapersonal modeling, deep learning on raw time series, and integrating environmental data, like room temperature, noise, and air quality, to build even more comprehensive models. In conclusion, this research demonstrates that wearable devices like Fitbits can serve as powerful digital phenotyping tools. With the right models, data aggregation, and feature engineering, we can detect mental health challenges with remarkable accuracy. F1 scores up to 0.83, using passive, unobtrusive data. This isn't science fiction. It's the future of mental health care, continuous, accessible, data-driven, and student-centered. And it starts with the data we already have, on our wrists every single day.